Und dann können wir weitergehen zum nächsten Vortrag. Und zwar hören wir in dem mehr zur deutschen Hyperspektralmission EnMAP. Über die haben wir ja schon an anderen Stellen im Tag etwas gehört. Nochmal zur Erinnerung, diese Mission ist im April gestartet und sie kann im Prinzip anhand eines spektralen Fingerabdrucks verschiedene Erdoberflächen charakterisieren und auch quantifizieren. Und Professor Sabine Chabrillat vom Geoforschungszentrum GFZ in Potsdam und der Leibniz-Universität Hannover wird uns jetzt einen Überblick verschaffen über die Entwicklung des Satelliten, über den aktuellen Stand der Mission und darüber, was EnMAP uns noch bringen wird. Sie wird auf Englisch vortragen und jetzt beginnen hoffentlich. Sie haben das Wort.
Yes, good afternoon everyone. And first, thank you for the invitation and the opportunity to present the EnMAP mission and especially the science potential of EnMAP here. So yeah, I'm merely a representative, and you can imagine there's several teams behind this presentation. So first, a general introduction. Yeah. Can you hear me now? Yes. Yes, so EnMAP is for environmental mapping and analysis program, and the core parameters they were defined since the start of the mission, based on the basically scientific goals. So every point on Earth could be imaged, except the polar areas. So it goes up to 77 degrees in latitude. There is a 30-meter pixel size, which makes it consistent with Landsat 8. There are 224 spectral channels, so it's a hyperspectral mission. And there is a revisit time of 27 days nadir, or there is an off-nadir option if you want more dynamic observations that allows to have much better revisit, like up to 4 days. So it is defined as a science mission. I think it's important to say it now, although we do see some commercial applications, and I think this will also develop. But from a definition of a mission, it's oriented towards science goals, and the goals are to measure key biophysical and geochemical parameters. It's also a highly calibrated mission, which also made some requirements on the design of the mission. And also data acquisitions are on demand, which means that it is not requiring the whole time. Basically, if you want a certain test sites, you have to make a request to the mission so that we acquire your area. And just to give a few data, I'm not sure it's so interesting for people, but basically you see, you have 11 o'clock is the revisit times. Here you see the spectral sampling interval, so less than 10 nanometer, and also very high radiometric accuracy. Okay, so yeah, what is hyperspectral? It's multispectral, it's optical remote sensing, so it's a passive technique. The only difference to usual multispectral satellites is that instead of having maybe 10 spectral channels, you have 200 very narrow spectral channels. And thanks to that, here, for example, this is a reflectance spectrum in the visible near infrared and in the shortwave infrared of a soil. And what is happening is that based on, instead of having just 15 points through the whole curves, which is what would happen with Sentinel-2, we have 224 points, basically. And here I should say this is a laboratory spectrum. So the atmospheric windows will remove this part. But basically from the signal, you can quantify and detect iron oxide content, you can detect organic matter, you can detect clay content, you can detect carbonate content directly from the signal. Yeah, so what a year for EnMAP, you have heard it. So my preferred picture here, EnMAP sit here. It was a ride-share mission from SpaceX with 39 other satellites. And here, this is just when it was opening before the release in the atmosphere. And already end of April, there was the first image acquired, which is, you see the Bosporus channels near Turkey. And you see, for example, different band combinations here in the visible, here with some near-infrared channels, and here with some shortwave infrared. And here are some examples of those first derivative products, like, for example, chlorophyll high content in the water. So this was very good. So now we are still in commissioning phase. There is 6 months commissioning planned. which we hope by end of October we come at the opening of the mission. So what makes EnMAP so special? With a detailed concept of instrument with two independent visible infrared and shortwave infrared spectrometer, and with this curved prism design, which is made to minimize keystone and smile. And also what makes EnMAP so special, this is this onboard calibration assembly, which is needed for the high quality data that we wish. So with a sun diffuser, also a dot spectral on for spectral calibration, and some other spectral spheres for linearity. So this is needed for the high quality data that we expect. And the second thing that is so special to EnMAP mission, this is the extensive science preparation program. So since more than 10 years, since maybe 2009, there has been an extensive science research project funded by DLR and supported by the BMWK, which says that right now there was several phases. You can see 12 years of science, major science research projects. More than 40 PhD students and postdocs were trained. It was a German program, so that means all those students were in German universities and German institutes. So right now we are looking at all these 40 persons. They are disseminated, they are professors in the university, in the research institutions. They are also through the Landesämtern. We have colleagues from the EnMAP program at BGR, Landesamt Geologie und Robo Boden, JKI, UBA. So there is a whole EnMAP community that is right now trained in hyperspectral remote sensing, and we are really hoping very much from this program. And the program was so training the user community and also looking at new applications and what can be done with hyperspectral remote sensing. So just to mention the two most visible, let's say, actions or results of this 10 years program is an EnMAP box. So it's a software toolbox that is available on the web. This is implemented in QGIS, so this is entirely online and free open source. So this is all the things in EnMAP followed the FAIR principle, which I think has been very important, and also because now it makes EnMAP being a model for the next mission preparations. Because now the NASA and ESA are planning a mission, and they also want to do like in EnMAP. So it was a unique in EnMAP. A second thing unique in EnMAP, or that EnMAP started, is HyperEDU. So this is an online education tool. So you can find several like slides collections. You can also find the first MOOC, so massive open online course. There are 1,200 people registered to this course online. And me now, each time I get a new student, the first thing I tell him is to do this MOOC. So, and the whole, it's internationally followed. So this is really something, big results of the EnMAP program. So just to mention a few words, a few applications. In geoscience applications, basically we have looked into the demonstration of potential for new Earth observation product. So for example, for soil mapping, we can quantify the clay content. Here, this is an example in the Terreno area in the north of Berlin, around Demmin, of soil organic carbon content. And you see a quantification here. It's an EnMAP simulation. This is not based on EnMAP, real EnMAP data. Here, it's an example of an application for geological mapping. So here, this is the results of a toolbox that is in EnMAP box. But also, we are looking at some new products for mineral exploration, so for prospection, looking at ore areas, because it was demonstrated that if we can map the surface geology, that we can make deductions of what is below it. And also something a bit more recent, but there's also some studies that demonstrate that we can map snow and ice properties, like in terms of grain size, instead of liquid water, and in terms of algae concentration. So we have several scientists at GFZ working in Greenland that are very much interested with this type of applications, and also looking at dust over snow, for example, in the Alps or in mountains. So now a few words about vegetation applications. This is also very wide. And here you have an example of a spectral information content, organic vegetation. If you have access to this signal, you can quantify the chlorophyll content in the leaf, the water content in the leaf. You can identify also if it was anthocyanin, the pigment concentrations, basically. Also some structural information. So based on this, there has been many and many applications of hyperspectral remote sensing for vegetation. But basically, it's like monitoring of a protected area, looking at, for example, foliar nitrogen concentration in forest. Here you see an example of forest mapping that was made in, like in an area near a tree. And also, there is also a very nice agricultural apps in the EnMAP box that was made by our colleagues from the LMU Mission. And for example, here it's a map of a chlorophyll A content in the leaves, and here a map of a leaf mass per area. Okay, so we looked also a bit at hazards and risk applications. So for example, hyperspectral benefits have a potential for a more distinctive characterization of predispositing factors. For example, for landslides, if we can identify the soil properties, maybe the type of vegetation cover, we can identify at which point the slope will break. For swelling soils, it's already proven. Spectroscopy can identify the swell potential. For land degradation, there are many applications because multispectral satellites confuse the signature of vegetation in an arid area, so those vegetations has no photosynthesis, so they look like a soil. And the hyperspectral remote sensing can make this differentiation very well. So you are looking at a better modeling of land degradation processes. And for volcanoes, we had big discussions because of those flank of volcanoes, they are very dynamic and they change geological composition. And for this, for example, hyperspectral is also very good. And then there are other applications on anthropogenic hazards and hazardous waste, thanks to this potential for identification of material. Now there are work that identify the type of plastics, work on several works on acid mine drainage mapping, like pH mapping for mine rehabilitation, and also several works on hydrocarbon leakage. So here, just to show an example, this is made with the Prisma satellite, so the Italian hyperspectral satellite, about methane mapping. So this is something a bit new. So methane has got an absorption band at 2.3 micron, which is at the edge of the sensor in terms of signal-to-noise ratio. But here it shows that it can detect large emissions of methane. So this may be something that EnMAP also will grow up, and we have to see how much we can do with EnMAP. So basically what we are looking EnMAP and support to EU policies. I think this will be very important and is the next step. So for example, the European Soil Protection Directive, we are looking at the mapping and monitoring of topsoils in terms of soil health and soil fertility. For example, the clay content is related to the water capacity of the soils, so related to soil fertility. There is this Dungenverordnung, so the fertilizer ordinance, and this is also linked to the quality of the soils. There's also the EU policies for sustainable raw materials, looking from prospections, rare earth elements can be detected with hyperspectral to mine sustainable, basically, exploitation. And with water framework derivative, so we already said it, we can map chlorophyll A content in water and sediment content. Yeah. We are looking also at, for example, for the global climate observation system, essential climate variables. So in this list of essential climate variables with, for example, soil carbon, which is really something where we can expect a better prediction from EnMAP data. We have above ground biomass, the land cover, topsoil moistures, and inorganic carbon in water. And also, basically, we are looking at the big goals of the UN Sustainable Development Goals, European Green Deal, where we really think that the EnMAP can provide something important. So just as a teaser before finishing, this is a very recent EnMAP image I think it was recently published. So this is Marrakech Ramon. This is the largest erosion crater, or one of the largest erosion craters in the world. And you can see, for example, one of those new Earth observation products that cannot be done now. And here, this is the amount of kaolinite at the surface. And you see here, this is an example of a signal of EnMAP at a high kaolinite-rich area and at a kaolinite-poor area. So in conclusion, this is the first German mission. We expect that the data will open to the public end of October, let's say early November. There has been this extensive exploitation program, which I think is very important because the legacy, in addition to all the software science tools, is that OHB is now building the next Copernicus mission, which is the SHAM satellite. GFZ and DLR are very much involved into this EU ESA missions too. And we have to see that EnMAP is a precursor of those future hyperspectral mission, and with EnMAP we can really do demonstrations of what will be the future Copernicus services, all in different geofields and key grid strategies, and looking at these next missions coming, and also looking at critical Earth system processes and materials. Yeah, I guess thank you to lots of people. Thanks.
Vielen Dank, Frau Chabrillat, für den Vortrag. Gibt es Fragen? Are there any questions? Okay, sieht nichts aus dann. Dankeschön.